In this lecture, we're going to continue on with the last of our three classic garbage collection algorithms, the copy collector. As we investigated last time, there are two types of allocators. The one we talked about last time was free list allocation, where we keep one or more lists of the free chunks in our process address space in the heap that we break pieces off from to allocate objects from. The copy collector is very different. It has an allocator called the bump pointer allocator. We're going to simply increment a pointer to get the next chunk of memory that we need for an object. The copy collector is a tracing collector. In its most primitive form, it is a stop the world collector. That is, it stops all mutators in order to perform copy collection. In this collector, we divide the heap into two halves called semispaces. One holds the data we're currently working on. The other holds data that is obsolete. That is, data we have scavenged. The roles of these two semispaces are flipped continuously. We allocate data from one semispace, called the from space, and when we run out of that space, we stop and we copy the live data from the from space to the other semispace called the to space, and then we update the necessary pointers and we restart the program allocating now from the to space, which we flipped, so it's called the from space. When we move from one semispace to another, we leave all of the dead data out in the old space. This data is called scavenger data or scavengers. This data is just abandoned. We don't clean it up. We don't put it on a free list. We just leave it out there. We're going to overwrite it the next time we use that space. Here's an animation of how copy collection works. We divide the heap in half. We're going to allocate from the from space. When the space fills up, we no longer can allocate, and we perform a garbage collection. By performing garbage collection, we're going to chase the roots and find all of our live objects. As we find them, we're going to copy them into the to space, also called the copy reserve. All of the rest of the dead data that we cannot reach, we leave out in the from space. They are scavengers, those objects. Then we do the flip and we start allocating from the from space. The advantages to copy collection is that we have this very, very fast allocation called bump pointer allocation. We simply increment a pointer to allocate new object space. There is no fragmentation because we are copying each time we flip the spaces so that we put all the objects together in one contiguous space, so all of our free space is also contiguous, avoiding fragmentation. The disadvantages, of course, are that we have to divide the heap in half, that we have to copy objects. And just because we've copied the objects and put them next to each other, we don't always improve locality, spatial or temporal, in the memory hierarchy. Here are the algorithms for the basic copy collector. You should be able to know and understand and reiterate all of them. If you look at the new routine on the bottom left, you'll see what I mean by bump pointer. In this new routine, this is the function that's called when an object is allocated by the program. We first check to see if we're out of space in the half that we're working at. If we are out of space, we're going to call flip and actually do the flip. If we come back from the flip and we're still out of space, we're then out of memory. Assuming this is all okay and we still have space in our from space where we're allocating from, we simply increment the pointer, that is the free pointer that points to the end of the allocated space where the free space starts. We simply increment that pointer by the size of the object that we're allocating and return the value, the address that we allocated from before we did the increment to the program. This bump pointer allocation is really fast because it's just a simple pointer increment. When we implement the flip, we have a more complex portion of the algorithm. You're going to be responsible for this portion of the algorithm as part of it'll be on the exam, so you'll be asked questions about it. So in this example, we have just run out of memory. We can't allocate a new object, and so we're going to perform the flip. We're going to flip from the from space to the to space. So the first thing we do is we chase our roots, and for each object that we can reach, in this case A, we're going to copy to the to space. When we make a copy of the object, we do a byte for byte copy of the entire object. In the old object, and we're going to call the new object A prime in this case. The old object A, in its header, we're going to use some of the header space for the address called the forwarding address of A prime. This way we'll know that A has already been copied, and we know where we copied it to because we've stored its address in the header of the object. So we're going to need space in the header for these addresses. Because we copied A byte for byte, the fields who are holding addresses, those addresses are still all pointing back to the addresses they were pointing to in the from space. So in this very first step, in the bottom right figure, the left most field of A prime is pointing to B, and the rightmost field of A prime is pointing to C. I just left off the actual arrows so that we could so it wouldn't get too cluttered. In the next step, we're going to chase all of A's children. And again, I'm just going through the algorithm in the copy function in the top right of this slide. So our next step is to chase all of A's children and to move them. So we first chase A's left child, which points to B, and we copy it. We put the address of B prime, that's now in the to space, in the header of B. This is called B's forwarding address. B has one field and it's a scalar, and since we copied it byte for byte, that scalar has been moved to the to space. So we're done with B, and we recurse backwards. We then chase the next child of A, which is its right field, which points to C. We copy C to the to space next. We then update C's header with its forwarding address, which is the address of C prime. We then, since we've copied byte for byte all of C, the fields of C prime point to the same addresses as the fields of C do. We then chase C's children, in this case D. We copy D, we copy D to D prime, we put D prime's address into the header of D. We copy D byte for byte, so its scalar value is 2, and we have no children to chase because it has no fields that have references in them. So we're going to recurse backwards. Upon recursing backwards, we're going to return D prime's address. This causes C prime's left child to be updated to refer to D prime instead of D. We then chase C prime's right child. C prime's right child points to A. Since A has already been moved, we notice that it's been moved because A's header has a forwarding address. So instead of moving A again, we simply return its forwarding address, that is, the address of A prime. So that causes C prime's right child to now point to A, and we recurse backwards, updating all of the other children accordingly. In this algorithm, we are performing a depth-first traversal and copying the children in depth-first order. We could have done it in breadth first order. Another name for the breadth first algorithm is called Cheney's algorithm. In this case, we move the roots to the to space. We then scan from left to right, moving objects in the from space to this to space and updating the pointers. You need to be able to show how the algorithms for depth first traversal and breadth first traversal work in a copy collector for a flip. The strengths of copying collection have led to its widespread adoption. The data is compact, there's no fragmentation, so allocation is very efficient. It's a bump pointer, and we don't have to worry about finding contiguous chunks of the heap space. We simply check whether we're out of space using a pointer comparison because we know where the end of the from space is. Copying collection handles variable size objects naturally, as well as objects with that are loops. So looped data structures are, it also handles pointer updates with no overhead, right? Pointer updates in the program itself are don't have to be modified in any way. Allocation is a simple pointer increment, and we eliminate fragmentation as mentioned earlier. The weakness, however, is that the address space is cut in half compared to other collectors. This is the primary drawback of copying collection. The other drawback is that we touch every page of the virtual memory, regardless of the residency of the program. So we use all half of memory, and then we copy all the objects to the second half of memory. By copying objects, we're using new addresses. By using new addresses, we're causing we're putting more pressure on the paging system of the operating system. We're also corrupting the cache of the program because we're touching all these new addresses and they're all going into cache. And then when we return back to the program's cache is no longer as it was and has to be refreshed with all of the new data. And this all causes overhead on the program. So when we're considering garbage collection, there's some considerations you should account for. There are the processing costs. How much does it cost to do allocation, to deallocate? How efficient is it on memory? Is there any kind of overhead on the program while the program is executing, like on pointer updates? The next thing you should consider when considering a garbage collector is what's its implementation? Is it easy? Is it complex? Is it simple? More complex collector may have bugs or may be harder to modify if that's what you're working on. Next thing to consider is the space overhead. How is everything kept track of in a collector? Next thing is heap occupancy and collector degradation. Reference counting provides no degradation, although there's fragmentation, and that may cause allocation to get slower and slower over time. For application where there's high residency in the heap, that is, the heap is full, mark sweep may be faster than copying because it has more heap to work with. Over time, copying collectors can thrash paging of the operating system because we're only using a portion of the heap and we're copying objects back and forth. Copying objects can be very expensive, and if you have long-lived objects, you're repeatedly copying them. Other things you should know about garbage collection is that there's these collectors called conservative collectors. And this is where we're trying to provide garbage collection for languages that we don't know which data values are pointers and which are not. And so these collectors cannot move objects because if we move objects, we have to go and update the pointer values to them. If we don't know what things are pointers, then we can't update those values because those values might be scalar and we don't want to cause the execution of the program to be invalid. We can use non-copying collectors for such conservative situations. Another situation where conservative collection might be necessary is where you have languages that pass objects to other languages. For example, Ruby passes objects, Ruby objects to C, or Python passing Python objects to C. Once those objects escape a language, you have no guarantee what was done with those objects outside, or whether they're being used or can be accessed. And so you have to be very careful with them. You can't go into that part of the program in most cases and update those addresses. So you have to be careful about those objects and not move them. You have to assume they're live. The other thing that's important about garbage collection is that there's potential for a garbage collector to actually do better than what a programmer can do in terms of performance. And the reason for this is locality. There are two types of locality, as you should know by now. Spatial locality, this is where an object is referenced. But when an object is referenced, the objects near it in space are also likely to be referenced. Temporal locality is a property where if you have an object that's referenced, it's likely to be referenced again soon. And our memory hierarchies in our architectures today take advantage of the principle of locality and our programs to provide performance improvements through caching. The garbage collection can hurt this memory hierarchy performance by hurting locality, but it can also improve locality by putting objects that are accessed together near each other. Beyond these three basic types of garbage collection, we can do better. The one way that most systems do better is by exploiting the observation that objects have lifetimes. The observation that I'm talking about is called the weak generational hypothesis. And this is where, on average, if you look at how programs behave and how they allocate objects and what the objects' lifetimes are, you see that most objects, those objects that have been recently allocated, die young. That is, objects that are recently allocated are likely to die, that is, become unreachable very soon. And this can range anywhere from 80 to 90%. And again, it's an estimate across lots and lots of different programs. And so if your program doesn't behave this way, you don't want to exploit this observation. But in general, this observation holds, and we can take advantage of it and improve garbage collection performance. So our goal is to make large heaps more efficient by concentrating our effort where there is the greatest payoff. And this is called a generational garbage collection. This is where we're going to exploit the lifetime of objects to make the garbage collection and the program's use of the memory hierarchy more efficient. The idea behind generational collection is that we're going to segregate objects by age with two or more heap regions. These heap regions are going to be called generations. We're going to have a young generation, and that's where objects are going to be allocated from. We're going to have older generations, and this is where objects that have been around longer are going to be copied to. And we're going to collect these generations, these heap regions, independently of each other and at different frequencies. We're going to collect the younger one more often because recently allocated objects, young objects, die often, so we shouldn't have to do much work there. Everything should be dead, and we should be able to move only the older objects, which should be few in number. We can do this as an incremental scheme, that is, to interleave garbage collection with the program's execution, or as a stop the world scheme. And there's different runtime systems that use both of these, not together, but certain runtime systems do one, others do others. Stop the world is always simpler, but incremental can reduce the pause time of programs. So the first thing we have to understand is how we're going to measure lifetimes of objects. We can't really use time because time is machine dependent and it depends on the speed of the machine. So an alternative to this is to you measure time or estimate time in terms of the number of instructions that are executed. But since we have different instruction set architectures, this may not be good because time will be different across these different architectures. So a second alternative, the one that's most commonly used, is to consider the number of bytes allocated so far by a program as time. since the program is typically going to, for the same set of inputs or the same user interactions, is going to allocate the same number of bytes regardless of what machine it's on underneath, what it's running on, is going to be the same, then this could be a good measure of time. It's not an exact measure of time, but it provides a good measure that's more portable across systems. So with generational GC, we have some examples here. We divide the heap into multiple regions. On the left, we have the old, and on the right, we have the young. We're going to allocate from the young region. The young region is sometimes called the nursery. And we're going to focus on the youngest generation, the nursery, to recycle objects, because if things die young, then there should be very little in the young space when it fills up to move to the older space. We collect the young generation by tracing the roots. Any of the roots that we find that are reachable, we can move to the old space. This is called promotion. Since, again, there should be very few objects that are promoted because most objects die young, the amount of time we spend here should be short. So we'll collect the young generation, the nursery space, often, and we won't collect the old space very, very often. So we'll repeatedly collect the young space, constantly, continuously moving anything that lives past through the allocation of a full young space. We'll move that to the older generation, and we'll call that tenured garbage. A collection of the young space is called a minor collection, and a collection of the entire heap is called a major collection. So just to summarize, allocation always happens from the young space, except for maybe large objects. That's kind of a special case. We're going to frequently collect the young space with minor collections, and every so often and very infrequently we'll collect the entire heap, and that's going to be called a major collection. We can use the different fundamental algorithms for either type of these collections. We could use mark sweep, copying, or some combination of the two. We always have to promote from the young space to the old space, so that's going to be a copy. We can have more than 2 generations as well, since it just depends on whether that's going to make sense for the program. And again, we decrease the frequency with which we collect as we move to older and older spaces. The one hiccup with generational collection is the fact that we want to collect the young space or the nursery separate from and independent of the old space. In order to do that, we have a problem, because there might be some objects in the old space that refer to young objects. That is, the old space might have objects that have fields that we have, that the program has modified to point to young objects. There's not usually too many of these, but we need to take care of them. So if we chased all the roots, we would find them, but we don't want to chase all the roots, because it defeats the whole purpose of only collecting the young space. So we only want to chase the roots into the young space, but we have to catch the pointers from the old to the new then, if we don't chase all the roots. The way we do this is that we put a check called a write barrier on all of our pointer stores in the program. That is, we introduce instructions overhead in the program that checks pointer stores, all of them, and it checks if the object on the right-hand side is in the old space, and what it's going to refer to is on the left-hand side of the assignment is in the young space. Then we need to remember this edge between the old and the young. We can remember the source object, or we can remember the address itself. It doesn't matter, but what we need to do is add these remembered objects to what's called a remembered set, and this remembered set is going to become part of our roots. Again, remember, our roots are our CPU registers, our physical registers, locations in our runtime stack for our local variables and parameters, and our globals, our statics table for Java virtual machines. We add to this triple the remembered set. That is, all of the addresses that point from the old to the young, or all of the young objects that are referred to by old objects. So, question to you is, do we need to remember the young to the old objects? The answer is no, because anytime we want to collect the old space, we might as well just collect the young space first, since doing so is fast. We'll collect the entire heap. We'll do the young space and we'll trace everything so that we can collect the old space. So we don't need to have a write barrier from young to old. Keep track of those because we'll catch those when we perform a full heap collection. There's lots of ways of implementing write barriers, and I've mentioned a few, but no matter what, all write barriers are going to be added overhead to the program itself. So there's some other generational considerations for garbage collection. There's some other considerations for generational garbage collection. That's this mutator cost. The number, if you have a lot of pointer stores in your program, then you're going to have increased overhead because we have to track these old to young references. We have an issue of how small to make the nursery or how big to make the nursery, because that's going to dictate how often we collect the nursery. If we make it too small, we're collecting a lot, but we may do it before objects have a chance to become old. That is, we may move garbage. So if we make the nursery too small, we may move objects that are just about to die, that truly are young. We may move them into the old space when really they're young objects. So we want to wait. We want the nursery to be big enough to ensure that objects are given enough time to distinguish whether they're going to be old or young. And this is just hard to do. If you, again, make them old too early, you have garbage sitting in the old space. That's pretty much like leaked memory, and you're going to have to perform a very slow full heap collection to get that memory back. If you make the nursery too big, then you're going to spend a lot of time copying objects back and forth, thinking that those objects are just about to die. And this is called the pig and the snake problem. When a snake eats a pig, that big old snake has to be digested and it rolls down the body of the snake. The same thing happens with multiple generations. As you copy these big, large objects, you just keep copying, and that copying is a waste. If you could figure out what the lifetime is an object is, and you don't even have to know lifetime, you just have to know whether an object is going to be old or young, so that you could put it into the space directly, you can avoid this problem. The other consideration is, how are you going to collect the individual spaces? The nursery could have no collector. That is, as soon as the nursery fills, we're just going to move the objects via copying to the old space or the mature space. We could, though, use copy collection in the nursery, copy objects back and forth to give them a chance to die before we move them to the mature space. In the mature space, we could use mark sweep collection or copying collection. And if we have multiple additional regions, multiple mature spaces, we could do different things for each of those spaces. So the questions for you are, how many generations should there be? How big should the generations be? And how can we make things more efficient? These are all the subjects of the research that has been done over the last decade in the garbage collection area. There's two advanced GC topics that we won't go into detail in, but you should know about: parallel collection and concurrent collection. Parallel collection is where we have multiple threads in the garbage collector. Parallel collection says nothing about stop the world or concurrent. It just says that when the garbage collector executes, it has multiple threads to work with. Think about this. The garbage collector chases all the routes. You could have different garbage collection threads chasing different routes at the same time, so that you can trace live objects quicker. You can also do scans of the heap quicker with multiple threads. Concurrent collection is the alternative to stop the world collection, and this is where we interleave garbage collection with program execution, so that only every once in a while do we have to pause to clean up all of the garbage, the remaining pieces of garbage that we can't guarantee that can be collected. In the Sun Open JDK and Hotspot garbage collection that is now owned by Oracle, there's a generational Mark Sweep Compact garbage collector. The idea here is, in the nursery you have an Eden where you allocate objects from, and then you copy it back and forth in the nursery following Eden allocation. And then there's a mature space that is used Mark Sweep, that is collected via Mark Sweep with compaction, region by region compaction. Instead of doing the entire mature space at once, we do it incrementally. And so it's a complex combination of all of the garbage collection techniques that we've seen so far. We can even get more advanced, and there's tons of work in this area. You can break up the heap into regions and be much more intelligent about what you're collecting and when. The IMIX collector is a really good example of this. You can also have the runtime system work more closely with the operating system and collect things on the basis of pages, operating system pages, and take advantage of the paging system to make your garbage collector more efficient. An example of this is the mapping collector. If you're interested in these garbage collection techniques, you can learn more by Googling IMIX or mapping collector.